Okay, today we're going to talk about the effect of core charge on atomic radius. We're going to do this by looking at the second period of elements in the periodic table. So firstly, we start by looking at lithium. Now lithium, the nucleus has a 3 plus charge. When we start to put electrons into the first shell around the nucleus, we get 2 electrons into that shell, and as a result, these electrons shield the nucleus, so any more electrons being added to this element will be entering from the second shell, and they will see an effective charge of 1 plus. We call this a core charge. So in lithium, the overall core charge is 1 plus. If we now look at beryllium, or start going across the periodic table, once again we fit 2 electrons into our first shell. That's all we can fit there. This once again shields the nucleus, so any electrons entering our second shell will see a core charge of 2 plus. In the case of boron, we put 2 more electrons into our first shell, and we have a 5 plus nucleus, so there is an overall core charge of 3 plus left over. Carbon, once again we get 2 electrons into that first shell, and the remaining core charge is 4 plus. Interestingly, the core charge does match the amount of valence electrons we would normally have in a naked atom. So, just to quickly finish them off, nitrogen has a core charge of 5 plus, and oxygen has a core charge of 6 plus, and in the case of fluorine, once we shield the nucleus with 2 more electrons, we are left with a core charge of 7 plus. Okay, as we've discussed, the core charge increases as we go across the periodic table. However, what does that increase in core charge, what's the effect that has on the actual size of the atom, or how does that actually affect the valence shell of electrons, which is the most important part of an atom in terms of chemistry? For this, we're going to demonstrate with our good friend here the effect of what would happen to the valence shell with an increasing core charge. His hands in this case represent the valence shell of an atom. So if we measure the distance there, it's approximately 30 centimetres. Now you're going to provide the same amount of resistance each time. So the first thing we will do is put a single elastic band. Now this represents a 1 plus charge. So you can feel there's a little bit of drag associated on those hands there, pulling them a little bit together. As we go across the periodic table to beryllium, we are now adding a second charge, and you can see his hands are pulled together slightly closer. This is in the same way the valence shell will be pulled in slightly closer by an increased core charge of 1. If we continue across to boron, where we now have a 3 plus core charge, you can see that his hands are somewhat pulled closer together again. If we continue to carbon, our core charge is now increasing. Hopefully that's not getting too uncomfortable for you there. So our core charge is 4 plus, and you can see the outer valence shell is shrinking and being contracted. We continue one more to a 5 plus core charge. We're now corresponding to nitrogen in the overall seam. You can see our hands are getting, our shells being contracted more, and oxygen a little bit more to 6 plus, and finally when we get to fluorine, where our core charge is now being increased to 7 plus. Through that process you can see that the outer shell, or the hands, have been contracted quite significantly, and if we measure that distance, we're down to 1/3 of the size. Thank you.